Right, well, good morning everyone, and thank you very much to the organisers for inviting me to this. Can everyone hear at the back? Yeah, good. Right, well, I've been involved with this activity for a major part of my career, and it's quite interesting that many of the issues that are raised today have been existing for a very long time. But this is a little bit of a history about how you get something into the field and some of the lessons that we learned along the way. Okay, that is something that was given to us nearly 25, 30 years ago. Now, I know that everybody's been concentrating on AT mines, but what I would raise is this is the sort of thing that you need to be aiming at. And it's got to operate in all of these conditions: high reliability, and certainly what we were told by the guys out in the field doing the work, they want something that can really operate 24 hours between charges. People want something that they can use for 8 hours. They don't want to be carting heavy batteries around. And the other thing that I haven't really put in there, the weight of this equipment should not be more for people who are handheld using this than maybe 2.5 kilograms. That includes everything. So that's the sort of ideal requirement that the end users have. When we first started this activity of looking at what would be suitable sensing techniques, I think the first conference was held in Stockholm somewhere in the beginning of about 1991, 92, and everyone went through a whole list of physics-based technologies that could be thought about. We looked at the physics and the application. Then we looked at the range and the probability of detection and the false alarm rates. And then we looked at the costs of these. And too many of these technologies cost far too much to actually be part of even a basic operator's business case, never mind a manufacturer's case. So all of this was looked at a long time ago. Now, the other thing that was particularly noticeable, and in those days I wasn't with the university, I worked for a company called ACRA Technology, later to become Cobham, was how the funding comes through from the military. If there isn't a war on, there's no funding. The minute somebody gets involved in a war, then the funding taps are turned on. And so the team builds up to a team that's a decent size, and then the war finishes and the taps go off again. Until, excuse me a minute, let's get rid of this. Until, of course, somebody gets involved in the next war and they realise they haven't got the kit that they need, and so the funding taps turn on again. So there's this stop-go in terms of funding. Apart from the fact, of course, you've also got, if you like, non-military campaigns which affect things as well. So one of the difficulties that we found in the technologies that we looked at and in the development was keeping a group together with this stop-go funding. That was a real issue. So it's something that needs to be thought about. What is sad to relate is that landmine casualties, I'm sorry this is not up to today's, but this was the latest I could find at the moment. Casualties are going up again. So, you know, it's very sad to note that. But we concentrated on the anti-personnel mine rather than the anti-tank. And this is the real issue, that for, if you like, production type anti-personnel mines, this is what they cost to buy, this is what they cost to clear. So this still remains the issue. And as people have pointed out before, it's the males that get hurt on this. And this is what happens to the vehicles. Sorry, it seems to do this sometimes. Now, if I can just comment on this because I've seen examples of vehicles that have been damaged recently. I was in contact with a company in South Africa. This is a publicity thing on their part. But if you can just bear with me on this.
Landmines and unexploded ordnance left behind by warring countries and terrorist groups have created a severe problem. Millions lie undetected in rural areas and even cities all over the world. Landmines and unexploded ordnance not only inhibit troop deployment and the supply of humanitarian aid, but also put operations personnel and civilians at risk. The removal, disarming, and destruction of landmines and unexploded ordnance is a difficult and dangerous task that takes years to complete. It requires highly trained personnel and specialized equipment.
Now, one of the things about that company, they developed a vehicle with a V-shaped hull which would actually cope with the explosion of 2 or 3 anti-tank mines underneath it. And those vehicles, of course, were bought by the military. But what is still surprising is that we're sending out Land Rovers in regions that actually have anti-tank mines, when potentially there was a solution that Mechem and the South Africans had developed probably about 25 years ago. So that, I'm not quite sure why we're still doing that, because there are solutions. There are vehicles out there that can stop this. And the other issue that remains, sorry about this, it's irritating. The other issue that remains is that there are still far too many people that are not signed up to the Ottawa Treaty, certainly for AP mines. ATs are different. When we first got involved with this, the complexity of trying to get an equipment specification that said clearly what we should be building, confronted with all the different operators on this, was quite significant. But eventually we did come down to one. I'd also like to point out that non-metallic mines have existed since the Second World War. The Germans made a device called a Toft mine, which was completely non-metallic. So this problem of the difficulty in finding certain types of mines has existed for a long time. You all know about AP mines, I won't want to spend a long time about that, and about AT mines. So these are typically the devices. When I hear these comments about drones and robots, that's an AP mine with bamboo growing up around it. You know, you're not going to get into that sort of thing easily at all. So technology solutions have to take into account the terrain. This is the terrain in Cambodia. This is the sort of target that you're looking at. And one of the other threats, IEDs, these are the components that you're looking for as well, and at different burial depths. So when we looked at this as an issue for building equipment as a company, there are the business requirements, the investor, the sponsor, and the customer business needs, what the end user wants as a piece of equipment, and then what system performance and what system function and system attributes you have. Because if you're going to build a piece of equipment, it can't just be a research equipment, it's got to be something that's fielded, that's reliable, that's robust, and can be produced. And one of the things that we found too often, and huge amounts of money was spent in the 80s and 90s. The Americans must have put something in the region of $120 million at least into R&D, and the same amount of money was put in by the European Union. And too often, solutions were at a very low technology level. They weren't proven, their performance wasn't established, and I think it left a bit of a bad taste with many of the end users, because when these things got out to the field, they really weren't up to the job. So we have to be very careful, and this is a comment particularly for academia, academia has to be particularly careful not to confuse something that's at a very early TRL level with something that's ready for field use. That's really important. Now, one thing we have to remember is that all of these things, whoever is funding them, at the end of it, unless there is money devoted to this, most industrial organisations have to make a profit out of building equipment. And the problem that you've got is any product life cycle follows these usual constraints. And the one thing again I would point out to my academic, well I'm in academia, but I would still point it out. The cost of research is almost nothing compared with the cost of development, or the cost of test and certification. When you turn something into a product, that's where the costs really come in. And it has to be borne in mind. And the other thing, of course, is the marketing budget has to take all this into account as well. So research is just at the very first stage of this. And you tend, with most projects, and this is a sort of a typical one, you start spending money and you don't actually break even until 2 or 3 years down the line from when you've actually got this through research and you're then going into production. So in that period, there is a board of directors saying to you as the project leader, you're carrying on losing money, it's ebbing away, when are you going to make some sales? When am I going to get a return on my investment? And again, we go back to this. Typically, for most of the sensors that we've got, with GPR, metal detectors and everything else, you have to get close in. You've got to clear the ground of vegetation. If the ground surface is rough, it causes problems for these sensors. And metal detectors have got a false alarm rate, which is something in the region of maybe 1 in 300 to 1 in 1,000. That's the problem with metal detectors. Well, the company I work for, ERA, first started in just after the Falklands War. And we built some radar systems. And we put them on vehicles, and the then signal processing had to be with big, almost HP semi-mainframes that was housed in one of these vehicles. It was the only way you could do the signal processing. And then MOD said, well, actually, it's going to be a lot cheaper to fence the fields off in the Falklands. We can't keep giving you guys the amount of money that we're giving you. So they fenced the minefields off, and the tap went off. However, we did have some other programs, and we carried on doing work on the GPR, and we developed GPR to an extent where we could find AP mines. This is a typical AP mine. There's the reflection back from the GPR, these are cross scans. And we got to the point where we could start to image. This is a typical AT mine with 3 fuses, and you can see the 3 fuses there. We were starting to get to the point where we convinced ourselves this was a viable technology, and we could build this together as a dual sensor, and there was some credibility. We also developed this as a commercial product for a GPR for detecting things in the road and all sorts of other things, and we mounted this on an early robot. This is an Alvis wheelbarrow used by the MOD, and we put one of our first antennas on there, and we could get it to scan. So remember, this is all in 1997, so it's going back quite a way. At the same time, we teamed with a company called Thales, part of Thomson CSF, and we looked at the market for humanitarian mine detectors, and my view is, I don't think this is dramatically changed from when we came to these conclusions. Both companies did separate break-even costs, and essentially this was my analysis. We wouldn't actually start to break even until 7 years after we started the project. And that's a hard sell to a board of directors, that paper's still available. It was one of the SPI conferences, but I'm going to highlight the key points on this. I'll keep a note on my time. New technology will only be accepted if it provides a significant improvement in detection performance at an affordable cost and it's easy to use. We looked at the whole market for detectors. And the replacement market was in the order of 3,000 units a year. This is for metal detectors, which we based this analysis on. We did it a whole number of different ways. We looked at Frost and Sullivan market analysis. We looked at this one. And we came to a really key conclusion about this. Anybody that's involved with this has to have the capability to design, produce, deliver and support to meet the environmental EMC performance and reliability standards needed for demining products. That's key. The end users were not going to accept this unless they were absolutely convinced that this was going to be a reliable technology. And I would back this up. A means of detecting explosives is highly desired by the end user. And the unique nature of the humanitarian demining, it doesn't meet the normal criteria for commercial investment decisions. So it has to be looked at a totally different way in terms of its economy. Well, by then we were supported by the UK Department for International Development, 2003. I'll skip, we'd worked with them by then over 3 years. We built units, we trialled it in various countries. We'd done trials in the UK, in Bosnia. We'd been to the States, we'd used some of their test fields. The US Army had built test sites with 1,000 samples, so we were able to get some statistical confidence of what the performance of the detectors were, what it was going to do. And we'd done work with Bactec in Lebanon. So we had a prototype system. The guts were in the backpack, that's the head at the bottom. We'd taken it to Bosnian trials with S4, we let people use it. We listened to what they said about, the weight of the handle, the ergonomics of it, how we provided the information to the end user. And remember, when we're designing, the end users were only worried about, are you going to detect a mine and do you not have a false alarm? And these were all of the design parameters for the GPR, but I suggest they're the same for every detector. Some things are under our control, all the green things. Those things on the right-hand side, we can't control that. We have to live with those and we have to design around them. So we then started to rebuild the system, and we eventually recorded a thing called Minehound, single board. We reduced the weight and the size of the GPR electronics. We modified the head design. We got the power down to 6.5 watts. We improved the sensor design. One of the things that the end users told us, they don't like round heads. They like thin, narrow heads because they can get into places with that. We redesigned it, re-engineered it, built it. That's what it looks like. I'm just going to pass over this in the interest of time. We did 3 sets of trials, one in Bosnia, one in Angola, and one in Cambodia. The big stars are the places we went to. Well, you all know this background, so I'm skipping over that. This is the sort of conditions we were in Bosnia. We went to Angola. That's the background from the civil war in Angola. These are the sites. What we did in each country, we took the equipment, we handed it over to the NGO there. We trained a group of the people on how to use it, and then we had outside observers monitoring the trials, saying, because we needed to step back from that so that there was legitimacy in the end of the trial results. So we had ITEC who were doing the monitoring. We went to Cambodia. Yeah, that's the issue with the Cambodian civil war. These are the field conditions in Cambodia. We built a beautiful training site in the morning, and in the afternoon, that's the training site. So these are the field conditions that you get in Cambodia. And we also went to Lebanon. We were working with a company there, Bactec. Southern Lebanon is under Hezbollah control. In those days, we didn't have to do risk assessments, which was just as well. Lebanon, these are the kind of soil conditions and the rocks that you get. Now, of course, rocks are quite nice big targets for GPR, so that was a good testing site. The end result was, we built these systems. It was found that for both APs, ATs, and improvised explosive devices, they work really well. So the US Marines bought this and completely re-equipped themselves with mine hats. And most of the NATO forces in Afghanistan followed suit. So of course the company were delighted because they'd never expected an outcome like that. We then also did some more trials in Cambodia where units were kept, and Michael is a joint author there of a paper that we published on that. What we found on these trials, to start off with, the performance of the operators was not as good as at the end of it when they've got really used to it, and basically the clutter, the reduction in clutter gradually increased over the 3 years. The same system was taken to Afghanistan, and this is the amount. Much better there because I think in Afghanistan most of the mines were AT mines, weren't they? Yeah. So we actually got, what they were doing is they were scanning the ground, marking them with the metal detector, then going back over with the GPR and saying, yeah, that looks to us as though it's a mine. And we were able to reduce the false alarm rate from the metal detector. We also built systems, and I'm going to try and get this one going. We also built systems for road clearance, and this is one of our early prototype systems, which hopefully will all work nicely. Right. Okay, we mounted this on a Land Rover. This is early field trials. What you'll see on this side, these are the landmines that were put in, some marker points, more landmines. So it's possible to use GPR with a reasonable ground clearance on that. So we built that system for road clearance as well. So that's something that is possible. We hope that we might be able to see at least the larger of the AP mines with that, but I think the trial results put that idea back in the dustbin again. Let's close this down. That's the typical sort of plot we had on one of our own trial sites. On the right-hand side are non-metallic mines. On the left-hand side, they're metallic mines at different depths. In summary, as far as GPR is concerned, there's a lot of research and development. The physics is well understood. It's being used now as joint systems quite successfully. What I should mention also, that for the sake of impartiality, the American H-staining system is also well used in the field now, and there's sort of comparable performances with the two. So for AP mines, equipment is available, but not really at the price the NGOs want. It's still far too expensive, which is where Find a Better Way at the University of Manchester is going, because what we're trying to do there is to basically develop a system which can be produced for quite low price. At the moment, unlike NQR, GPR systems are detection systems. They don't actually analyse, but there is the information in the GPR signal and also in the metal detection signals, which is what Manchester's working on, to actually classify the mines. You can use a spectroscopic metal detection approach, which then can classify the type of metal within that's being detected. And for the GPR, certain types of target have resonances, natural resonances, and they can be exploited. So GPR can find resonances. What humanitarian demining or road clearance needs are low-priced systems. It's logistics economics. But I would say one final thing, I'm just going to pass on from that, because we've not got enough time. at the moment. Okay. I'll just leave this thought with everybody. So, although landmines are a problem, I think with a lot of developing countries, I think this has to be seen in context as well. So, thank you very much indeed.
Thank you very much. Questions? Okay.
Thanks. Well, first thing, I found the middle part of the presentation about the GPR and the development of the GPR very, very interesting. Although when you did your business model and the payback of 7 years, I don't quite understand when you've sold 18,000 units to the US military why they can't be priced slightly better now. I think there's been a return on investment and there could be a return of some humanitarian dividend from that.
Can I just answer that question? I have retired from ERA Cobham. You will have to address that comment to their directors, not to me.
Or I'll buy shares.
Yeah, it's a fair comment.
The last point about road casualties is absolutely fine, but I mean ultimately why do we clear mines? And it's because there are other reasons than that. But the issue I have with a number of the early part of your presentation was the reason. How much do you think a vehicle with a V-shaped hull costs today if you go out and order one?
I don't know, but it is
about $500,000. How much does a Land Rover cost?
Okay. But are there ways in which you could actually, modify some of these vehicles instead of actually going out
and Halo too, but I've just spent $20 million buying V-shaped hulls for peacekeepers in Mali. But you can only buy so many, and they cost an awful lot of money.
Yeah.
Again, the Americans have 2,000 of them parked on the Kuwait border if they wanted to donate them.
But then what you're saying is it does come back to the funding. There are some solutions to try and ease these problems. It's a funding problem.
Yeah. If GPR wasn't $15,000 a detector, we would get a lot more done with them.
Okay, it's the one thing that I'll hold my hand up. I started out, I wanted to see these things produced at about typically the same as a metal detector.
Well, Guy Willoughby gave you that spec because I heard him gob off 20 years about it. 99.6 has not been an international standard for clearance for over 20 years. That means you're prepared to miss 4 in every 1,000 mines. I've chaired the IMAS review board for the last 7 years. We do not accept 99.6 as a UN standard.
You don't accept it?
No.
But that's what the UN says.
No, it isn't. I work for the UN. I head the UN's mine operations. We haven't said it since IMAS came out in 2001.
Right.
So you're 20 years out of date on that one.
Well, okay. So what is it now then?
There isn't. You clear to the standard required for the site, which is to remove all threat.
So you're saying 100%?
No, I'm saying you remove the threat to the level that you're confident that you'll issue a clearance certificate on, and the clearance certificate is issued by the host government. So it's acceptance of risk.
Right. So what does that actually mean?
It means what the person on the ground is prepared to accept. So you have your checks and balances, but 99.6 was a meaningless number anyway, because it meant you could miss 4 in every 1,000 mines. That's why we stopped using it.
I'll bow to your, that was what people were working. This is a historical.
Yeah,
it
is.
But
the scene you set, and this is why I'm challenging it, is very out of date.
Okay.
There weren't 110 million mines at the peak of it, and there certainly aren't now.
No, agreed.
So by giving that impression, it shows that nothing's been done in the last 20 years, in a sense. Because you name me 3 countries that have really significant mine problems, other than North-South Korea, the Cambodian border, and Western Sahara. There are not big minefields left in the world, and this is one of the challenges in developing the technology. There isn't a market for it because the problem has been pretty much addressed. And now the problem is from IEDs. In Afghanistan, 95% of casualties last year did not come from traditional minefields.
Yes.
So your numbers of casualties going up is absolutely right, but it's not coming from mines.
Right.
It might be coming from victim-operated devices, but it's not mines.
Fine. No, I mean, I'm perfectly happy to accept. This was basically a history of how it started up, what we were given, right, and how it all moved through. So, that's the history.
Okay. Any other questions or comments? Okay. Right. Thank you very much again.